Okay, 7.1, number 39 is a little bit tricky. This is the problem as it exists, as it's written right here. And in looking at it, I thought that it was a good candidate for integration by parts. We've got two distinct parts to the integrand, and given that they're both first degree linear functions, I didn't really think that the derivative of one would match up with the other, so I looked at it and thought integration by parts would be the way to go. So went through it and felt pretty good about my decision right here. We let u equal the x up on the top and dv equaling the square root of the 1 plus the x plus 1 on the bottom. This is a little messy, but didn't think it'd be that hard to integrate. So taking a look right here then, differentiated u and just got a dx right there. Took the antiderivative of the dv here and increased our exponent by 1 to a 1/2, divided by that 1/2 to put a 2 out in front. So looking at all of that then, the original integral then got rewritten as, here we go, u times v, so that's a 2x times the integral of x plus, or excuse me, times the square root of x plus 1, minus the integral of a v times a du. So there's a 2 right there. We have the integral of x plus 1 to the 1/2 and the dx there. And this certainly looked easier than the original integral we were dealing with, so I thought we were in pretty good shape. So for that answer, the uv remained intact. Again, doing this integral here, we increase the exponent of 1/2 to a 3 over 2, divided by that 3 over 2, which is to multiply by 2/3, and this existing 2 times that 2/3 got us a 4/3 out in front. So that is what I felt pretty good about for my answer here to doing this problem with integration by parts. Only problem was, this was an odd, and as a lot of you guys saw, when you look this up in the book, they didn't have an answer that looked very much like that at all. So let's take a look at what the book did here to get their answer. What they did instead, and if you looked at the solutions manual you saw this, is they went u substitution with this one. And it was a method that hadn't occurred to me at first, but it is something that shows up in a few problems, so it's probably worth revisiting. So what they did is they decided to let u equal the radicand in the denominator, something that we did kind of a lot. So u was just the x plus 1. Du then simply becomes dx. So that right there takes care of our primary substitution right here. The dx is going to get replaced by a du, but it still leaves an x here that we have to account for. So if we took the original equation right here of u equals x plus 1 and simply solved it for x, we got x is equal to u minus 1. So the full substitution then would look something like this. The denominator, which was the square root of x plus 1, now just becomes the square root of u. The numerator, which was just an x, gets replaced by a u minus 1, and the dx at the end gets replaced by a du. Now, the trick we would do well to remember here would be to realize that we've traded here taking a monomial over the square root of a binomial, and we've traded that for a binomial divided by the square root of a monomial. It doesn't seem like a whole lot of progress here, but then you remember the idea that you're allowed then to take a binomial over a monomial and split it up into two different terms. So we have the u over the square root of u minus the 1 over the square root of u. And now just rewriting that a slightly different way, this was u to the first divided by u to the 1/2 power, which just gives us a u to the 1/2. This one was just a u to the negative 1/2, and this wasn't that bad to anti-differentiate. The 1/2 becomes a 3/2, dividing by that gives us a 2/3 out in front. That negative 1/2 power, when we integrate, becomes a 1/2 and a 2 out in front. And then we go all the way back now to the original substitution value for u and put that in right here and find that, there we go, this is the answer we came up with right here. Got a 2/3 x plus 1 to the 3/2 minus a 2 x plus 1 to the 1/2 plus c. Now that's all well and good and makes a lot of sense until you unfold this highly technological piece of work right here and realize that the answer that we came up with over here doing it by integration by parts doesn't really seem to match their answer that they came up with doing u substitution. Now, one thing we should know by now is that if both methods work, they should get us the same correct answer. And it certainly looked right here like that was not the case. But if we do a little bit more digging on this, this has a happier ending to it than we might think. So the question at hand right here, everybody, is our answer that we got from integration by parts equal to the book's answer that they got by doing u substitution? Well, a couple things to notice. First of all, they both have an arbitrary constant added on both sides, so we can just subtract that out from both sides and be done with that. Then, each side of the equation has an x plus 1 to the 1/2 power, and each side has an x plus 1 to the 3/2 power term. So we're going to try to combine those. And what we're going to do is take this x plus 1 to the 3/2 term with a negative coefficient and add it over here to the right. And then we'll take this x plus 1 to the 1/2 term with a negative coefficient and bring that one over here to the left. Now, this is the tricky part right here. When we put together these two terms, they both have a common factor of x plus 1 to the 1/2, and what's left then is going to be the 2x, and remember that this will be a plus 2 when we bring it to the other side. So that's where this comes from. It's the combination really of this term and this term put together, and we factor out the x plus 1 to the 1/2, leaving us with a 2x plus 2. The rest of this is pretty easy now. That minus 4/3 gets added over here to the 2/3 to make a new coefficient of 6/3, which is going to get us 2x to the x plus 1 to the 3/2 power. And the last thing we have to realize right here is that this binomial has a common factor of 2. So we're going to factor out that common factor of 2, which leaves us a new binomial of x plus 1, which sure enough can be combined with this one. That power right there is 1, so when we add these two exponents together, that gets us 2x plus 1 to the 3/2, which is exactly what we had over there on the right-hand side. So, long story short, both of those two methods, integration by parts and u substitution, are going to get us the same solution here, and both of them are equivalent to one another.